13.8 billion years ago, something impossible happened. The entire universe burst out of a space smaller than an atom, igniting time, matter, and reality itself. But here's the twist. Scientists now believe the Big Bang wasn't the true beginning. Before that cosmic eruption, there existed something stranger than emptiness. A quantum void humming with invisible energy. A place where the laws of physics were still being drafted. Today, we're diving into colliding dimensions, endless cosmic cycles, and the shocking idea that nothing might be the most powerful force in existence. If you're ready to see how reality built itself from the impossible, hit like and subscribe. Let's jump in. Imagine the darkest corner of space. No stars, no planets, no light, just endless black. Now here's the discovery that flipped physics on its head. That emptiness is an illusion. When scientists examined the vacuum using quantum mechanics, they found something astonishing. Empty space isn't empty at all. It's alive with energy. Think of the ocean on a calm day. From far away, the surface looks flat. But up close, small ripples constantly rise and fall. The quantum vacuum behaves exactly the same way, except the ripples are invisible waves of energy that exist everywhere. Always. This isn't theory. This is confirmed science, proven in labs across the world. Physicists call this background buzz zero-point energy, the lowest possible energy state that space can have. You can't drain it. You can't shut it off. It's built into reality itself, and it gets even stranger. This energy does things. When two metal plates are placed extremely close in a vacuum, they're pushed together by an invisible force created by differences in vacuum energy. This phenomenon, the Casimir effect, has been measured with incredible precision. It proves that nothing actually has structure, pressure, and properties we can measure. Ancient philosophers believed that removing all matter from a region of space gave you true nothingness. Modern physics disagrees. If the vacuum contains energy, then no part of the universe is ever truly empty. Every cubic inch of space is filled with this silent hum of quantum activity. When you move your hand, you're passing through an invisible ocean of energy that existed before the first star and will remain long after the last one fades. But measuring this energy revealed a problem so big it still haunts physicists. Today, when scientists calculated how much energy the vacuum should contain, the answer was absurd: 120 orders of magnitude larger than what we observe. That's like predicting someone weighs 10 pounds and discovering they weigh less than an atom. The mismatch is so enormous that it's been called the worst theoretical prediction in physics. And it tells us something profound. We still don't truly understand what nothing is. The quantum vacuum doesn't only hold energy, it creates matter. Right now, in the tiny space between your eyes and this screen, particles are popping into existence from nowhere. They exist for fractions of a second, then disappear. These are virtual particles, and their effects have been measured with stunning accuracy. Here's what happens. Energy and matter are interchangeable. Einstein proved that the vacuum is full of fluctuating energy, and sometimes a fluctuation becomes large enough to form a particle and its antimatter twin. Like an electron and a positron, they appear, live for an unimaginably short moment, collide, explode into pure energy, and vanish back into the void. This cycle repeats trillions upon trillions of times every second in every tiny pocket of space. The vacuum isn't still. It's a raging storm of creation and destruction happening beneath the fabric of reality. And we know these virtual particles are real because they leave fingerprints. In the 1940s, physicists studying hydrogen atoms found that the electron energy levels didn't perfectly match predictions. The mismatch was tiny, but it was real. After years of intense investigation, physicists finally realized what was causing the strange behavior in hydrogen atoms: virtual particles. These ghost-like particles briefly interact with electrons, shifting their energy by a tiny but measurable amount. This phenomenon is known as the Lamb shift, and it proved something extraordinary. The vacuum isn't passive. It's alive with quantum activity, and the evidence only gets stronger. Virtual photons, particles of light that flash into and out of existence, create an effect called vacuum polarization. They temporarily shield the electric charge of particles, subtly changing how forces behave at the smallest scales. Without virtual particles, the equations of quantum physics wouldn't work. They're not an optional detail, they're fundamental to reality. Now, think about what this means for the idea of nothing. If the vacuum is constantly creating particles, even for trillionths of a second, then absolute nothingness is impossible. Nature simply won't allow it. Chaos is built into the foundation of the universe. But here's where the mystery deepens. If tiny virtual particles can appear from the vacuum, what stops a larger fluctuation from appearing? What prevents the vacuum from creating something that doesn't vanish, something permanent? The answer lies in a principle that makes nothing even stranger than it sounds. In 1927, German physicist Werner Heisenberg discovered a rule that shattered ordinary logic. You cannot know both the exact position and momentum of a particle at the same time. Measure one precisely, and the other becomes uncertain. This is not a flaw in our tools, it's how the universe works. Now, apply this idea not to particles, but to energy and time. The uncertainty principle allows energy to fluctuate wildly, as long as the fluctuation is very brief. The shorter the moment, the larger the allowed energy spike. This is why virtual particles exist. The vacuum can borrow energy to create them, then repay the debt so quickly that the universe's bookkeeping stays balanced. And here's the crucial insight. The uncertainty principle guarantees that the vacuum can never be perfectly still. There will always be fluctuations. Always perfect nothingness is forbidden. To have true nothingness, you'd need to know the exact energy at the exact time, and nature simply does not allow that information to exist. Imagine trying to photograph a hummingbird's wings in mid-flight. All you get is a blur. The quantum vacuum is the same, except instead of motion blur, you get energy blur. The vacuum constantly bubbles with possibilities that never settle, and this has staggering implications. If true nothingness is impossible, then before the universe existed, the vacuum wouldn't have been empty. Quantum fluctuations would immediately erupt. Energy would appear. The void would become unstable, and scientists have measured this instability when they cool matter close to absolute zero. The coldest temperature possible, quantum fluctuations don't disappear. They're the only motion left. Atoms still jitter. Fields still wiggle. You can remove heat, remove particles, remove light, but you can't remove quantum uncertainty. This isn't speculation. Physicists have directly detected these fluctuations by watching how they perturb electrons and trigger spontaneous photon emissions in atoms. The evidence is overwhelming, But this leads to a profound paradox. If nothing cannot exist, then something must have existed before the Big Bang. Either the universe is eternal, or it emerged from a quantum state that was never truly empty. But there is a third possibility, one that sounds like sci-fi but may be true. Imagine standing on a frozen lake. The ice looks solid, but underneath, the water is slightly warmer than it should be. The ice is stable, but not truly stable. Physicists call this a state. Now imagine the vacuum of space behaving the same, weighed according to quantum field theory, supported by particle accelerator data. The vacuum can exist in different energy levels. There is a true vacuum, the absolute lowest energy state, and false vacuums, which sit at higher energy levels but can remain stable for immense periods. Our universe might be sitting in a false vacuum right now, and that idea terrifies some physicists. A false vacuum is if a large enough fluctuation occurs, it can suddenly decay into a true vacuum. When that happens, a bubble of true vacuum forms and expands at the speed of light, rewriting the laws of physics as it grows. Everything inside it changes. Matter dissolves, forces shift, reality resets. Catastrophic, but also illuminating. What if the Big Bang was exactly this event? A false vacuum collapsing into a true vacuum, igniting our universe. This idea has mathematical support through the Wheeler-DeWitt equation, which describes how quantum states evolve when gravity is involved. In 2014, physicists in China found solutions showing that a tiny bubble of vacuum could spontaneously appear from quantum fluctuations, and under the right conditions, it wouldn't collapse. It would expand. It would inflate. It would become a universe. The false vacuum preceding our cosmos would have been unimaginably small, smaller than an atom, perhaps even as tiny as the Planck length. 10 meters at that scale, space becomes grainy. Quantum mechanics rules everything. Cause and effect blur. Events can happen without causes. Fluctuations can create structure. We see these behaviors every day in particle physics experiments. This isn't imagination. It's how the quantum world works. Extrapolating this behavior to the origin of the universe requires a leap, but it's a leap firmly grounded in established science. The idea of a metastable false vacuum gives us a picture of a pre-banged reality unlike anything we imagine. There were no swirling clouds of gas, no early matter, no ticking clock. There was only a quantum state hovering in an unstable configuration, waiting for the single fluctuation that would ignite everything. But how do we know this quantum energy does more than just exist? Because energy has weight. It curves space-time, and the vacuum's energy is no exception. Einstein's equations tell us that both mass and energy generate gravity. A ball of gas does. A beam of light does. So does the invisible energy of empty space. This prediction has been tested repeatedly. Vacuum energy appears in Einstein's equations as the cosmological constant, a number describing how much energy exists in every cubic meter of empty space. For decades, scientists assumed this number was zero. They were wrong. The discovery that shattered cosmology in 1998. Two independent teams of astronomers studying distant supernova discovered something impossible. The expansion of the universe is accelerating. Galaxies today are flying apart faster than they did billions of years ago. But that makes no sense. Gravity should slow expansion down. Matter attracts matter. Left alone, the cosmos should be maybe even collapsing. But the data showed the opposite. Something was pushing space itself apart. The only explanation that fits. The math is vacuum energy, a small but non-zero energy. Density inside empty space that produces repulsive gravity. The more space expands, the more vacuum exists, and the more repulsive force it generates. A runaway effect. Scientists call this phenomenon dark energy, and measurements now show it makes up about 68% of the universe. Think about that. More than 2/3 of reality is made of energy in empty space. All the matter we see, stars, planets, galaxies, contributes less than 5%. This discovery transformed cosmology. The vacuum isn't a stage where events unfold. It's an active player that shapes the universe's destiny. It bends space-time. It steers light. It determines the ultimate fate of everything. These measurements aren't guesses. The Planck satellite mapped temperature patterns in the cosmic microwave background and precisely confirmed dark energy's strength. Ground-based telescopes measured how galaxies cluster and found the same result. Independent methods, different instruments. Same answer: empty space has power, real, measurable, universe-shaping power. So what did this vacuum energy do at the beginning? If vacuum energy dominates the cosmos today, imagine what it could do at the moment of creation. That leads us to the most important event that occurred before the Big Bang. Everything you've heard about the Big Bang is incomplete. The hot, dense fireball that formed atoms and released the first light was not the beginning. It was the aftermath. Before, it was an event called cosmic inflation. Inflation. The real beginning developed in the early 1980s by physicists like Alan Guth and Andre Linde. Inflation describes a period of unbelievably rapid expansion that occurred before the classical Big Bang. During inflation, the universe doubled in size again and again, expanding faster than light, faster than anything normally allowed. And here's the crucial point. Inflation solves problems the old Big Bang could not. For example, the universe is shockingly uniform. Galaxies separated by billions of light years have nearly identical temperatures and densities. How did regions that could never have communicated end up so similar? The old model had no explanation. Inflation provides one. If the universe began far smaller than expected, then inflated to enormous size in a fraction of a second, distant regions we see today were once neighbors. They equilibrated early. Then inflation stretched them across the cosmos. The proof lies in ancient light, the cosmic microwave background. Its tiny temperature variations match inflation's predictions with stunning accuracy. The pattern of hot and cold spots looks exactly like stretched out quantum fluctuations frozen into spatium. But here's the revolutionary part. Inflation happened in a universe that was cold and empty, powered entirely by vacuum energy, the same kind of vacuum energy we observe today. This energy triggered exponential expansion, doubling the universe's size again and again. 1 gives 2, gives 4, gives 8, gives 16. Like pennies doubling on a chessboard. Inflation involved at least 80 doublings, possibly hundreds. A region smaller than a grapefruit ballooned into something larger than the observable universe. All in less time than it takes light to cross an atomic nucleus. When inflation ended, the vacuum energy didn't vanish. It transformed. Its energy converted into a flood of particles and radiation. That transformation was the Big Bang. The heat, the density, the primordial plasma, all of it came from the decay of the inflationary vacuum, scale beyond human intuitions. Saying the universe doubled 80 times sounds simple. It's not. Each doubling multiplies size by 2. 80 doublings mean multiplying by 2 a number with 24 digits. The universe ballooned by a factor of more than a septillion in about 10 seconds, a decimal point. 34 zeros. And then a 1 dot to grasp that scale. Imagine a virus particle, too small to see even with powerful microscopes, inflated through 80 doublings, and it would become larger than the entire observable universe. That was inflation, and it works scientifically because it solves real, observed problems. One is the flatness problem. Space can curve like a sphere, curve like a saddle, or be perfectly flat. Measurements show our universe is astonishingly flat. If you fired a laser across the visible universe, 93 billion light-years, it would barely bend. The old Big Bang couldn't explain this. Inflation can dart tiny. Deviations from flatness in the early universe should have grown huge over billions of years. Left alone, even the slightest curvature should have magnified into something obvious. We should live in a cosmos that bends dramatically, but we don't. Inflation solves this by stretching space so violently that any initial curvature was ironed out. It's like blowing up a balloon. The bigger it becomes, the flatter any small patch of its surface looks. Another puzzle is the horizon. Light has only had 13.8 billion years to travel since the Big Bang. That means parts of the universe separated by more than 13.8 billion light-years have never exchanged information. Yet when we measure them, they are identical. Same temperature, same expansion history, same physics. How did they synchronize? Inflation gives us the answer. Those distant regions were once close together, close enough to reach the same uniform state. Then inflation tore them apart faster than light could reconnect them. The uniformity we observe today is the frozen memory of their early contact, and the evidence backing these 80-plus doublings continues to strengthen. Satellite missions have mapped the cosmic microwave background with astonishing precision. Its pattern of temperature ripples matches inflation's predictions exactly, so precisely that the data stunned researchers. Competing theories that avoid inflation fail the moment they confront observation. The math shows inflation must have lasted long enough for at least 80 doublings, and possibly thousands. We don't know the exact number because we can only observe a finite patch of the whole. Inflation may have expanded space far beyond our cosmic horizon, creating regions forever hidden from us. This means the universe you can see, every galaxy, every star cluster, every photon is just one tiny fragment of a reality vastly larger, and all of it emerged from a cold, empty vacuum expanding faster than physics normally allows. So what powered that impossible expansion? For decades, popular science portrayed the Big Bang as the moment when time, space, and matter burst into existence from nothing. That picture is outdated. Modern cosmology tells a different story. The Big Bang was not the beginning. It was a transition. It was the moment when the energy driving inflation decayed into matter and radiation, flooding the universe with heat. A phase transition, like water boiling into steam, but on a scale that reshaped existence itself. We know this because theory and observation align. The cosmic microwave background, the universe's oldest light, shows us what things looked like 380,000 years after the Big Bang. It's almost perfectly uniform, with tiny fluctuations exactly where inflation says they should be. But here's the key. Insight. When we follow Einstein's equations backward in time, we don't hit a true beginning. We hit a wall, a point where densities and temperatures become so extreme that our equations stop working. This mathematical breakdown is called a singularity, but it's more accurate to call it the edge of our understanding. Inflation rewrites this picture. Instead of time beginning at the singularity, time already existed. Before the Big Bang, the universe was cold and empty, filled only with vacuum energy. Clocks ticked. Space expanded. Cause and effect operated normally. Then inflation ended. When it did, the vacuum energy that had been fueling expansion had to go somewhere. Energy cannot simply disappear, so it transformed. It decayed into particles, quarks, electrons, photons, neutrinos, all moving with incredible energy. Their collisions produced heat. Within the first second, temperatures soared to 10 billion degrees Celsius. Too hot for atoms. Too hot for protons and neutrons to remain free. Only the most fundamental particles could exist. This seething plasma of energy and matter is what we call the early Big Bang universe. But that heat didn't exist during inflation. Inflation was cold. That difference matters. The Big Bang wasn't the start. It was the aftermath. We've traced this transition using both theoretical models and experimental data. Particle accelerators like the Large Hadron Collider recreate miniature versions of the early universe, confirming our equations and giving us a window into the physics of that primordial plasma dot. So the timeline becomes clearer. First, a cold quantum vacuum. Then, inflation, stretching space exponentially. Then, the vacuum energy decays into heat and particles. The true Big Bang. After that, cooling, atoms, stars, galaxies. So when did time actually begin? We still don't know. Perhaps during inflation, perhaps before. We've pushed the boundary of the unknown backward, but not erased. It and the evidence continues to strengthen. There's a smoking gun in the data proving the universe existed before the traditional Big Bang. It's hidden in the cosmic microwave background. There, called superhorizon fluctuations. The cosmic horizon marks the maximum distance light could have traveled since the Big Bang. Anything beyond that distance has never been in causal contact. The standard Big Bang model predicts that temperature variations in the early universe should not appear on scales larger than this horizon. Anything larger than the cosmic horizon represents regions of space that should never have interacted. According to the traditional Big Bang model, those regions shouldn't share coordinated patterns or matching properties. But that's not what the universe shows us. We observe fluctuations far larger than the horizon. Enormous, synchronized features appear in the data collected by WMAP, Planck, and multiple ground-based telescopes. The evidence is overwhelming. How do you get matching patterns across regions that have never communicated? There's only one possible explanation. Those regions were in contact before the Big Bang, during inflation when the universe was tiny, cold, and dominated by vacuum energy. Quantum fluctuations rippled across all of space. Inflation then stretched those fluctuations to colossal scales, far larger than the horizon we see today. By the time inflation ended and the Big Bang fired up, these quantum fingerprints were already woven into the fabric of the universe. They appeared as density variations in the early plasma, which today show up as tiny hot and cold spots in the cosmic microwave background, and the math leaves no wiggle room. Inflation makes extremely specific predictions about the correlation between temperature and polarization, how fluctuation sizes vary with scale, how uniform but not perfectly uniform the spectrum should be. Observations match these predictions with breathtaking accuracy. In 2003, the WMAP team released the first high-precision maps showing the exact correlation patterns inflation predicts, including features on scales. The classic non-inflationary Big Bang model predicted something totally different. The data crushed the old model and confirmed inflation 20 years later. Even more precise instruments have strengthened the case. The Planck satellite mapped the cosmic microwave background with such stunning accuracy that inflation's predictions can now be tested to fractions of a percent. Every test passes. Correlations appear exactly where they should. This is one of the most powerful pieces of evidence in all of cosmology. The patterns in the sky cannot exist if the Big Bang were a true beginning. They demand an earlier phase, inflation, when the universe was smaller, colder, and governed by physics we've only begun to understand. Think about what that means. We've moved beyond guessing about before the Big Bang. We now have observational evidence of what happened before the hot Big Bang stage. The oldest light in the universe carries information from a time preceding the classical Big Bang. The universe keeps secrets, but it also leaves clues. The cosmic microwave background, released 380,000 years after the Big Bang, has been traveling to us for more than 13 billion years. It gives us a snapshot of a baby universe, hot, dense, and simple. But hidden inside that snapshot is something deeper, a fossil record of the inflationary epoch. Here's how. During inflation, the vacuum energy that filled space behaved quantum mechanically. Like all quantum fields, it fluctuated randomly. These fluctuations were microscopic, smaller than atoms, but inflation magnified them. It stretched tiny quantum ripples into density variations, spanning millions of light years. When inflation ended and the Big Bang transition occurred, these variations became permanently imprinted into matter and energy. Regions with slightly higher density eventually grew into galaxy clusters. Regions with slightly lower density became cosmic voids. In other words, the cosmic web, the entire structure of the universe, emerged from quantum noise. The cosmic microwave background captures this information because its photons passed through a universe already molded by these density variations. Hotspots come from slightly denser regions. Cold spots come from slightly emptier ones. The pattern we see today is a fossilized map of conditions created during inflation. Scientists have measured this map with astonishing detail. Temperature variations are tiny, only a few parts per 100,000, revealing a universe that was almost perfectly uniform, with just the right amount of structure to eventually form stars, galaxies, and life. These variations produce a specific distribution called the power spectrum. Inflation predicts that the spectrum should be nearly meaning fluctuations of different sizes should have almost the same amplitude. Observations confirm this with remarkable precision. It has become a foundational pillar of modern cosmology, but the microwave background carries even more information. It also shows polarization, the orientation of the ancient photons, electromagnetic waves. This polarization pattern is influenced by gravitational waves, and inflation predicts that it should produce gravitational waves as a byproduct of its violent expansion. Detecting these primordial waves is one of the biggest goals in cosmology. Finding them would reveal inflation's energy scale and give us a glimpse of physics far beyond what particle accelerators can achieve, even without a direct detection. The data already rules out many inflation models and narrows down the possibilities. The cosmic microwave background has become our laboratory for probing the universe before the Big Bang. With every improvement in measurement technology, inflation becomes clearer, and the pre-bang universe comes into sharper focus. What emerges is a picture of a universe existing in a state completely foreign to our everyday experience. We assume time flows in one direction, from past to future. We remember yesterday, never tomorrow. Causes come before effects. It feels fundamental. But what if time itself only began during inflation, or even later? This idea is no longer wild speculation. It all begins with taking Einstein's general relativity seriously. Einstein showed that space and time aren't separate entities. They're woven together into a single four-dimensional fabric called space-time fabric that bends, stretches, and curves. Gravity isn't a force acting within space-time. Gravity is the curvature of space-time. This leads to something profound. Time is physical. It's part of the universe, not a stage outside of it. So when we ask, what happened before the universe existed, we might be asking a meaningless question, something like, what's north of the North Pole? Stephen Hawking explored this idea using quantum mechanics. Working with James Hartle, he proposed the no-boundary hypothesis. In this model, the universe is described using imaginary time, a quantum concept where time behaves like another spatial direction. With this, the universe has no sharp beginning. It doesn't start at a single point. Instead, it smoothly transitions from a timeless quantum state into the classical space-time we experience. Think of Earth as you travel south. You eventually reach the South Pole. Beyond that, there is no more south. You've reached the boundary of the concept itself. The no-boundary model suggests something similar for time. If you trace the universe's history backward, time curves in such a way that there is no before. The timeline simply ends without a beginning moment. But not everyone agrees. Physicist Julian Barber argues that time is an illusion, a byproduct of how matter rearranges itself. In his view, only the present truly exists. The past is just a record stored in the way particles are arranged right now. The future doesn't exist yet. In this picture, asking about before the Big Bang is meaningless for a completely different reason. Yet both perspectives might be partly correct. At everyday scales, time behaves normally. Clocks tick, causes create effects, and the arrow of time moves forward. But at quantum scales, especially near the universe's origin, time becomes fuzzy and uncertain, just like position or momentum. During cosmic inflation, if it happened, time likely operated in a familiar sense. The vacuum energy driving inflation could persist for a measurable duration. Space could expand over time, but before inflation, our understanding collapses. The singularity predicted by general relativity signals the breakdown of the theory itself. We need a true quantum theory of gravity, and we don't yet have one. We can only trace cosmic history back to the Planck time, 10 seconds after the Big Bang. Earlier than that, physics as we know it fails. What does before even mean when time itself is emerging? This is where language becomes our enemy. Every word we use before, cause, beginning assumes time already exists. If time was born with the universe, these concepts simply don't apply. Cosmologists struggle with this constantly. They have to describe experiences outside human intuition using vocabulary built for human intuition. One solution is to abandon before entirely. Georges Lemaitre, who first proposed cosmic expansion, called the universe's origin a day without yesterday. Centuries earlier, St. Augustine said that time was created along with the universe. Modern physics gives this ancient idea mathematical form. Space-time is a manifold with boundaries. Time could simply end at the Big Bang the way Earth's surface ends at the poles. Asking what's before the boundary is like asking what color is Tuesday. But quantum mechanics might offer a loophole. Particles can tunnel through barriers they shouldn't be able to cross. Electrons tunnel through walls. ALPHA particles tunnel out of atomic nuclei. It's a real, observable effect. Some physicists propose that the universe itself, tunneling into existence, is a similar quantum event. Alexander Vilenkin developed this idea. A universe with zero size has a tiny probability of tunneling into a state with non-zero size. Once it does, inflation blows it up into a cosmos. Here, there is still no before in the usual sense. But there is a prior quantum state, a timeless vacuum from which the universe emerges. Time begins only when classical space-time forms. David Bohm's interpretation of quantum mechanics gives yet another picture. In Bohm's framework, particles always have definite positions, guided by a quantum potential. When applied to cosmology, this idea suggests the universe could have definite properties even at creation. The quantum potential behaves like a cosmological constant, driving early expansion. These models remain theoretical, but they point towards something deeper. Maybe before the Big Bang doesn't mean earlier in time. Maybe it means prior in a different sense, logically prior, causally prior, quantum mechanically prior. The state from which the universe emerged might not exist at an earlier moment. It might exist entirely outside the framework of time. This challenges everything our intuition expects. We're used to thinking of existence as something that happens in time. But quantum states don't necessarily exist in time. They exist in configuration space, a mathematical landscape describing all possible arrangements of the universe. The Big Bang might have been a transition from one configuration to another, with time itself arising during the transition. Philosophers have debated this for thousands of years. Now physics lets us make those debates mathematical, testable, and grounded in evidence. We may never have a complete answer, but our questions are getting better, and the ideas go even further. Some theories suggest our universe didn't appear from nothing, but from a collision, a cosmic impact between colossal structures in higher dimensional space. This leads to the ekpyrotic model, born from string theory, where particles are vibrational patterns on tiny strings instead of points. The deeper we look, the stranger and more beautiful the universe becomes. String theory suggests that the universe has more dimensions than the familiar three of space and one of time. These extra dimensions might be curled up too small for us to detect, or vast and hidden from our perception. In some versions of the theory, our entire universe exists on a three-dimensional brane, floating inside a higher dimensional realm. Imagine a sheet of paper suspended in a room. You can move around on the sheet, but you can't step off it. Meanwhile, the room around the sheet contains directions and dimensions you can't access. That's how our universe might exist inside a higher dimensional reality. In 2001, physicists Paul Steinhardt and Neil Turok proposed the ekpyrotic model, a radical rethinking of cosmic origins. In this model, two enormous parallel branes drift in higher dimensional space. They attract each other over unimaginably long periods. Slowly, almost imperceptibly, they move closer until they collide. From our point of view, confined to one brane, this collision would look exactly like the Big Bang. A surge of energy floods our universe. Matter and radiation fill space. Expansion begins. The universe heats, cools, and evolves, yet it was not a true beginning. It was a cosmic crash. The ekpyrotic model solves several problems that inflation struggles with. It naturally explains why the universe is so flat and smooth. The slow, steady approach of the branes irons out irregularities long before impact. It explains the patterns in the cosmic microwave background as vibrations created during the collision. And unlike some inflationary models, it avoids the multiverse problem. Inflation tends to produce an infinite number of bubble universes with random properties. That makes it extremely hard to test, because any observation can be explained away as we live in a lucky bubble. Ekpyrosis sidesteps this. One collision creates one universe, but the model has challenges. We don't fully understand what happens during a brane collision. String theory is still incomplete. Some critics argue a collision would destroy the smoothness the model depends on. Others say getting the right pattern of density fluctuations requires fine-tuned parameters. Still, the model remains scientifically plausible and testable. For example, it predicts extremely weak gravitational waves in the early universe, far too weak to detect in the cosmic microwave background. Inflation predicts stronger ones. Future observations may decide between them. The ekpyrotic model also contains something deeper: cycles. If two branes can collide once, they can collide again. After impact, they bounce apart, drift through higher dimensional space, and are pulled back together. Another collision. Another universe. Another Big Bang. This gives rise to cyclic cosmology, an endless sequence of cosmic cycles. From our perspective, the universe expands, empties out, and then through a higher dimensional collision begins again. This idea eliminates the infamous Big Bang singularity, the point of infinite density and temperature where physics breaks down. Most scientists think the singularity isn't real, it's simply the point where general relativity stops working. The Big Bounce provides an elegant alternative. Instead of originating from an impossibly dense point, the universe transitions smoothly from a prior existing phase into our current expansion. This concept is supported by another major theory of quantum: gravity loop, quantum gravity, LQG. In LQG, space itself is made of discrete, indivisible units like pixels on an ultra-tiny screen. These quantum chunks of space prevent matter from being crushed into an infinitely small point. There is a minimum size to the universe, a hard limit, when contraction pushes matter too tightly. Quantum effects create a kind of repulsive pressure, spring-like force that causes the universe to rebound. Calculations show that a collapsing universe in LQG would reach a maximum density, then bounce, expanding again. In 2020, researchers Robert Brandenberger and Ziwei Wang explored how such a bounce could create the universe we observe. They found that if the pre-bounce universe underwent slow contraction, a mirror image of inflation, it could generate the precise density fluctuations. Seen in the cosmic microwave background, this raises a remarkable possibility. The universe before the bounce might have looked like ours, but in reverse. Galaxies merging instead of drifting apart. Light shifting to blue instead of red. Time flowing forward for observers, then but appearing reversed from our perspective. When the bounce occurred, information from that earlier universe could survive the transition. Fluctuations in matter and energy could pass through, seeding the galaxies of our universe. The Big Bang, then, wasn't the beginning. It was a midpoint in a much longer story. Before our expansion came a contraction. Before that, perhaps another expansion. The universe might not be 13.8 billion years old. It may have existed indefinitely, infinitely far into the past through endless cycles. Cyclic cosmology avoids many philosophical issues with creation from nothing. There's no need to explain a moment when time itself suddenly switches on. There's no need for the universe to emerge out of a literal void. Instead, everything flows from previous cycles, governed by the laws of quantum gravity. Testing these ideas isn't easy. The bounce happened under conditions we can't replicate, and the physics is subtle. But the theories make clear predictions about gravitational waves, the cosmic microwave background, and the structure of the universe that ongoing experiments are actively searching for. If the cyclic picture is correct, the story changes. We don't need to find the beginning of the universe because there never was one. Instead, we must understand its rhythm, its expansions, contractions, and bounces in the most ambitious vision. The cosmos has no origin and no end. It is an eternal heartbeat, expansion, contraction, collision, rebirth. Each cycle lasting trillions of years. Each cycle giving rise to stars, galaxies, planets, and perhaps life. An eternal universe, endlessly remaking itself. Over trillions of years, the attractive force between the branes draws them together again. Eventually, they collide once more. Another Big Bang erupts. A new universe is born. But each cycle is not identical. With every iteration, the universe grows larger. The scale factor measurement of cosmic size expands exponentially from cycle to cycle. Entropy increases too, but because each universe becomes vastly bigger than the last, that entropy gets diluted. Nothing violates the second law of thermodynamics. The universe simply gains more and more room for disorder to spread out. This solves the classic entropy problem that destroyed earlier cyclic theories. In the 1930s, physicist Richard Tolman showed that a simple repeating universe would accumulate so much entropy that it would eventually fail to bounce at all. The Steinhardt-Turok model avoids this fate by invoking dark energy and ensuring each cycle expands more than it contracts. Another influential cyclic idea comes from Nobel laureate Roger Penrose. His conformal cyclic cosmology suggests that the universe expands forever until all matter decays into pure radiation. At that stage, nothing has mass. Everything moves at the speed of light. When there is no mass, the usual concepts of time, distance, and scale stop having meaning. In this strange future, Penrose argues, the infinite end of one universe can be mathematically reshaped into the Big Bang of the next. The transformation preserves geometry, even though the scale changes into conformal. In this view, time becomes circular, or perhaps a cosmic spiral, linking the end of one eon to the birth of another. These ideas remain speculative, but crucially, they are testable. Cyclic models predict subtle patterns in the cosmic microwave background. Some versions suggest that collisions or events in a previous cycle might leave circular imprints, ripples frozen into the ancient radiation. Searches for these signals have been carried out. So far, nothing conclusive, but the hunt continues. Cyclic cosmology has deep philosophical appeal. It removes the uncomfortable question of why the universe exists at all. In this picture, the universe simply is eternal, transforming but never beginning or ending. Existence becomes fundamental. The particular state of our cosmos becomes just one temporary phase in an infinite sequence. But the theory raises new mysteries. If cycles repeat forever, how many have come before? Does the universe retain any memory of past cycles? Do the laws of physics stay the same each time, more can they change? Here's a possibility that sounds like science fiction but comes from serious theoretical physics. Each cosmic cycle may operate under different physical laws. The constants that determine particle masses, the strengths of forces, and the behavior of the cosmos could shift from cycle to cycle. Why? Because in many theories, these constants are not fixed by deep principles. Instead, they arise from how quantum fields settle into their lowest energy states. It's like water freezing. The exact shape of the ice depends on small fluctuations. During a brane collision or a quantum bounce, the extreme energies could reset these fields. As the new universe cools, the fields settle into new configurations, new constants, new physics, a cosmos with properties unlike any that came before. This has surprising consequences. In most cycles, the constants might not allow complex structures to form. Stars may never ignite. Galaxies may never assemble. Chemistry might be impossible. These universes would be simple, cold, and short-lived. But occasionally, by chance, the constants land in the narrow range that allows atoms, stars, molecules, and perhaps life. We find ourselves in one of those rare successful cycles because we couldn't exist in any other. This is a cyclical version of the anthropic principle. The idea that the universe must be compatible with the observers inside it. Some scientists dislike this reasoning. It replaces one mystery, why are our constants life-friendly, with another, why do all possible constants occur across cycles? Others embrace it. If constants vary, we can make probabilistic predictions. We should expect to find ourselves in a universe that barely permits life, not one that is overwhelmingly optimized for it. Interestingly, some evidence supports this. The cosmological constant in our universe is extremely close to the maximum value that still allows galaxies to form. Much larger, and matter could never clump together. Much smaller, and we'd need to explain why it's not zero. We seem to be sitting near a boundary, exactly what cyclic anthropic reasoning predicts. Testing whether the constants changed in earlier cycles is extraordinarily difficult. A bounce would erase almost all information. Still, some theories suggest exotic features, topological defects in spacetime, might survive and leave telltale traces. More realistically, we can test whether frameworks that allow variable constants make sense. String theory, for instance, predicts a vast landscape of possible vacuum states, each with different effective physics. Understanding how transitions between these states might occur is an active area of research. The big picture, emerging from cyclic cosmologies, models where physics itself evolves, is both humbling and breathtaking. Our universe is not special. It is one outcome in an eternal process, a single chapter in a story that spans eons. The cosmos generates universe after universe, cycle after cycle, endlessly sculpting new realities. Most cycles of the universe never amount to anything. Most are failures. A few become strange and interesting, and once in an immeasurable while, a rare universe manages to last long enough to produce beings capable of asking these questions. What we're left with is a vision of reality, far stranger than the simple something from nothing story. There might be no ultimate beginning, no final ending, and no single set of physical laws, only an eternal churning of possibilities, with tiny, precious windows where complexity briefly blossoms, before collapsing back into simplicity, then rising again in a new form. In this picture, the universe isn't a creation, it's an endless transformation. Quantum gravity and the death of the singularity modern physics rests on two towering pillars: general relativity, the physics of gravity, black holes, and the expanding cosmos, quantum mechanics, the physics of particles, atoms, and the microscopic world. Both theories work flawlessly where they're supposed to, but at extreme scales, they clash violently. Loop quantum gravity tries to fix that conflict by quantizing space and time themselves. Instead of being smooth, space becomes a woven network of incredibly tiny loops, a kind of quantum chain mail. From a distance, it feels smooth, just like a TV screen looks, continuous until you get close enough to see the pixels. This redefines the Big Bang. In classical relativity, matter collapses into infinite density, a singularity, but loop quantum gravity says, no singularities allowed. Space has a minimum size. You can't compress it beyond the Planck scale, about 10 to 35 meters. When the universe contracts down to this limit, a new force appears. Quantum repulsion. Gravity flips. Instead of pulling inward, it pushes outward. The universe stops collapsing and bounces. A smooth quantum bridge connects a contracting universe to an expanding one. Not a beginning, a transition. And this isn't hand-waving philosophy. Detailed simulations using LQG mathematics show something incredible. The tiny fluctuations that eventually formed. Galaxies survive the bounce. Information passes through the transition intact. Abhay. Ashtakar's team at Penn State demonstrated that a slow, pre-bounce contraction produces nearly the same pattern of fluctuations we see imprinted in the cosmic microwave background today. This leads to a powerful prediction. A bounce should leave subtle fingerprints in the gravitational wave spectrum, slightly different from what inflation theory predicts. As detectors grow more sensitive, we might soon be able to tell the difference. There's a philosophical shift to loop. Quantum gravity doesn't need extra dimensions, exotic matter, or colliding branes. It simply applies quantum rules to space-time itself. The terrifying singularity disappears. It was never real, just a mathematical mirage, caused by using classical physics where it doesn't belong. Once quantum effects are included, the universe has no absolute beginning, just an eternal sequence of expansions and contractions, connected by quantum bridges. You no longer need to explain how something came from nothing, because there was never nothing. Did the universe create the conditions for its own existence? Now we reach one of the weirdest ideas in cosmology, and shockingly, it might be true. The universe may have set up the conditions that allowed itself to exist, a kind of cosmic bootstrap. Here's how, in quantum mechanics, the future can affect the past. This is known as retrocausality. When you measure a particle, you don't just reveal what it was, you decide what it was. Your measurement reaches backward in time and picks a history from the cloud of quantum possibilities. John Wheeler took this to a breathtaking scale. He suggested that the universe functions the same way. Observers don't just study the universe, they help bring it into being. He called this the participatory anthropic principle. The universe creates observers who look back at the universe's origin and through their observation help define which version of the past actually happened. It sounds mystical, but it emerges naturally from certain quantum interpretations. The universe's wave function contains all possible histories. When conscious beings appear and start making measurements, they collapse part of that wave function, selecting which cosmic history becomes real. In this view, the Big Bang wasn't a random event. It was the only beginning that could lead to observers who could eventually look back and make that beginning real. A causal loop. Observers exist because the universe had the right initial conditions. Those initial conditions exist because observers eventually arise. The loop closes consistently. No contradictions. James Hartle and Stephen Hawking explored this idea deeply in their no-boundary proposal. The universe, they argued, doesn't have one fixed past. It has a superposition of possible pasts. Our existence helps determine which path solidifies into reality, a universe that evolves, universes other thinkers arrive at. Similar conclusions from a different angle. Lee Smolens, Cosmological Natural Selection, proposes that black holes create new baby universes. Each baby universe inherits physical constants similar to its parent, but with small variations, over countless generations of universes. The ones most likely to survive are those that produce lots of black holes, which also happen to produce long-lived stars, planets, and life. We exist in one of these universes not by chance, but because only this type of universe gets selected in the cosmic evolutionary process. Why something exists at all these ideas remain controversial. Hard to test, mind-bending, but together they hint at a profound answer to the oldest question. Why is there something rather than nothing? Quantum physics suggests that nothing is unstable. Fluctuations constantly generate possibilities. Most collapse instantly, but occasionally a configuration arises that can sustain itself, expanding, evolving, persisting. We observe one of these rare, self-sustaining realities because universes that can't support observers will never be observed. The universe exists because it can exist, because the conditions that allow it to survive are the conditions it selects for through cycles, evolution, and quantum self-consistency. Reality may be a strange loop, a cosmic structure that continuously brings itself into being. And the mathematics, it gets even stranger from here. Most universes, if they exist at all, fail immediately. Some linger briefly. A rare few grow complex enough to produce observers beings capable of asking why any of this exists. What emerges is a vision of reality far stranger than the simple story of something from nothing. There may be no ultimate beginning, no final end, and no single set of physical laws, only an infinite churn of possibilities, with brief windows where complexity blooms before fading back into simplicity, then rising again in a new form. In this picture, the universe isn't a creation, it's an eternal transformation. Loop, quantum gravity, rewriting the beginning. Modern physics rests on two great pillars: general relativity, which explains gravity, black holes, and the universe's expansion, and quantum mechanics, which governs particles and the microscopic world. Each works perfectly in its domain, but at extreme scales, they clash. Loop quantum gravity attempts to unite them by applying quantum rules to space and time themselves. Instead of treating space as a smooth fabric, it describes it as a network of tiny discrete loops, like a chainmail mesh. At large scales, the mesh blurs into smoothness, just as a TV screen looks continuous from a distance, but pixelated up close. The key breakthrough comes when these ideas are applied to the Big Bang. In general relativity, the universe collapses to infinite density as singularity. But loop quantum gravity says space itself has a minimum volume. It can't be compressed smaller than a fundamental quantum of space that exists at the Planck scale, about 10 meters. When a collapsing universe reaches this density, a new effect emerges: quantum repulsion. Gravity flips from attractive to repulsive. Collapse halts and reverses. The singularity disappears, replaced by a bouncer-smooth quantum bridge connecting contraction to expansion. This isn't hand-waving. Detailed calculations and simulations show how a universe can evolve through such a bounce. Even more remarkably, the tiny fluctuations that seed galaxies, the cosmological perturbations, can pass through the bounce intact. Information survives. Abhay Ashtekar and colleagues at Penn State have shown that a slowly contracting pre-bounce universe could generate a nearly scale-invariant spectrum of perturbations. What we see in the cosmic microwave background, loop quantum gravity predicts that bouncers should also leave specific signatures in primordial gravitational wave signals future detectors may be capable of identifying. Unlike other cosmological models, loop quantum gravity doesn't need extra dimensions or exotic matter. It simply applies quantum mechanics to space-time. When we do that, the singularity evaporates. The universe has no absolute beginning or end, only alternating phases of contraction and expansion, stitched together by quantum geometry. This removes the classic creation paradox. You don't need to explain how something came from nothing. There was never nothing to begin with, only an eternally evolving quantum spacetime, a universe that creates its own conditions, what triggered our particular phase. One of the strangest ideas in cosmology may offer an answer, and it sounds circular, yet mathematically consistent. The universe may have created the conditions necessary for its own existence. Here's how. In quantum mechanics, the future can influence the past through retrocausality. Measuring a particle doesn't just reveal its state, helps determine what that state was. Observation reaches backward in time, selecting one outcome from many possibilities. John Wheeler expanded this idea to the cosmos. His participatory anthropic principle suggests that observers help define the universe's history. The universe produces observers who then look back at its origin and, through that act of observation, help determine which origin became real. The universe's wave function contains all possible histories. When conscious observers arise and make measurements, they collapse parts of that wave function, selecting the history consistent with their existence. In this view, the Big Bang wasn't random, it was the one history that could lead to observers capable of confirming it. Other possible initial conditions may have led to sterile universes with no complexity. Those histories were never chosen because no observers existed to collapse them into reality. This forms a self-consistent causal loop. The universe produces observers. Observers select the universe's past. the past leads to the observers. A loop with no contradiction. James Hartle and Stephen Hawking explored similar ideas in the no-boundary proposal, in which the universe doesn't have a single fixed past, but a superposition of possible pasts shaped by present conditions. Lee Smolin's cosmological natural selection offers another twist. Universes that produce black holes generate baby universes. Each new universe has slightly different constants. Over countless generations, universes optimized for producing black holes and therefore stars, planets, chemistry, and complexities. We live in such a universe not by chance, but because only such universes persist. Across these ideas, a single theme emerges. The universe may bootstrap itself into existence. Nothingness is unstable. Fluctuations that create self-sustaining structures persist. Fluctuations that cannot sustain themselves vanish. We observe a universe that sustains itself because non-sustaining. Universes never create observers. Reality becomes a strange loop that creates itself. Extra dimensions and hidden. Geometry we experience three spatial dimensions: left, right, forward, back, up, down. Add time, and we have 4. But string theory claims there are at least 7 additional hidden dimensions, for a total of 11. Why don't we see them? Because they're compactified, curled up, so tightly that they lie far beyond our ability to perceive them. Imagine an ant walking on a telephone wire. From afar, the wire looks one, but up close, the ant can explore its circular thicknesser, hidden second dimension. The extra dimensions in string theory work the same way, everywhere around us, but curled up at unimaginably tiny scales. Particles are strings vibrating through these hidden dimensions. Different vibration patterns appear to us as different particles: electrons, quarks, photons, neutrinos, everything. This leads to profound implications. Our universe may be a brane floating within a high bulk. Matter and light are confined to this brane, but gravity can leak into the extra dimensions, possibly explaining why gravity is so weak compared to other forces. In the ekpyrotic model, parallel branes drift through the higher dimensional bulk. When they collide, a big bang occurs. The pre-collision universe exists in this higher dimensional framework. String theory also predicts a vast landscape of possible vacuae, 10 or more ways to curl up the extra dimensions, each producing different physical laws. This ties naturally to the idea that constants may vary across cosmic cycles. Testing these ideas is hard. The required energies are far beyond today's accelerators. Still, hints may appear in gravitational waves or tiny deviations in how gravity behaves at small scales. LHC experiments have looked for missing energy that might indicate particles slipping into extra dimensions so far without success. But the search continues. Whether accepted or disputed, string theory's core insight remains. The universe we observe may be only a shadow of a deeper multidimensional reality, eternal inflation, a universe that never stops. Creating inflation was originally proposed as a brief burst of expansion after the Big Bang, but the mathematics suggests a far stranger outcome. Inflation may never fully end. A quantum field that inflated drives inflation when it sits at high energy. As it rolls downward, inflation ends and its energy turns into matter and radiation. Our Big Bang, but quantum fluctuations constantly jostle the field. In some regions, these fluctuations push it back up, reigniting inflation. Those regions continue inflating while others stop and form bubble universes. This creates a fractal multiverse of cosmic foam. Our visible universe is one bubble where inflation ended. Beyond our horizon, inflation continues, spawning new universes endlessly. Alan Guth and Andre Linde developed this framework in the 1980s, and it arises naturally from combining quantum mechanics with general relativity. Each bubble may have different physical constants, infinite universes each with different laws. We exist in one compatible with life because we could not exist in any other. This solves certain puzzles but raises new ones. If every possible universe exists, how do we predict anything? Some physicists propose counting which types of observers are most common across the multiverse, but debate continues. A key result from 2003 theorem shows that inflation cannot be eternal to the past. It must have begun. Something triggered it. What that was remains unknown. If eternal inflation is correct, nothingness disappears from the story. Reality becomes an infinite, self-reproducing structure. Pocket universes form within an eternally inflating background, each thinking it is the entire cosmos. The inflating background expands faster than light, hiding other universes forever. Nested inflation could even occur within a bubble universe, generating subbubbles and infinite hierarchy of realities. Max Tegmark organizes multiverses into levels. Level 1, distant regions of our own universe. Level 2, eternal inflation bubbles with different constants. Level 3, many worlds quantum branching. Level 4, entirely different mathematical structures. The eternal inflation multiverse. Level 2 is the most grounded scientifically. It doesn't rely on speculation. It falls out naturally from established physics. We experience 3 dimensions of space left-right. Forward, backward, up, down. Add time, and you get 4 dimensions. But string theory suggests there are at least 7 additional hidden dimensions, giving a total of 11. Why don't we notice them? The theory proposes that these extra dimensions are compactified, curled up so tightly that they're imperceptible to us. Imagine an ant walking on a telephone wire. From a distance, the wire seems one-dimensional, and the ant can only move forward or backward. Up close, however, the wire has thickness, allowing the ant to explore a second dimension along its circumference. The extra dimensions in string theory work similarly, existing at every point in our 3-dimensional space but rolled up at scales far smaller than atoms. Particles vibrate through these hidden dimensions, and different vibration patterns manifest as different particle types. An electron is one mode of vibration, a quark another. Photons, neutrinos, and all fundamental particles emerge from strings, vibrating through this higher dimensional space. This framework has profound implications for cosmology. Our universe could be a 3-dimensional surface embedded within this higher dimensional space. Everything we see, stars, galaxies, light, is trapped on this surface, but gravity behaves differently. Its effects can leak into extra dimensions, which may explain why gravity is so much weaker than the other fundamental forces. The epirotic model takes advantage of this idea. If parallel 3-dimensional branes exist within the higher dimensional bulk and can move through these extra dimensions, collisions become possible. Our Big Bang might then be the aftermath of such a collision, with the pre-collision state existing within the higher dimensional framework. String theory further suggests that different ways of compactifying the extra dimensions produce different physical laws. There could be 10500, 10500, 10500, or more distinct ways to curl up the extra dimensions, each generating a unique vacuum state with varying particle masses and force strengths. This vast landscape connects to the idea that physical constants might vary between cosmic cycles. Testing these concepts is extraordinarily challenging. Probing the extra dimensions directly requires energies far beyond anything achievable with particle accelerators. Yet indirect evidence might exist. Gravitational waves traveling through the higher dimensional bulk could carry subtle signatures, and tiny deviations in gravitational behavior at small scales might reveal the geometry of these hidden dimensions. Experiments at the Large Hadron Collider have searched for signs of extra dimensions by looking for missing energy in particle collisions, energy that could escape into the bulk, but so far, no definitive signals have been found. String theory remains incomplete and controversial. Some physicists embrace it as the leading candidate for a theory of everything, while others criticize it for its lack of testable predictions and the fine-tuning it requires. Yet the central insight endures. The universe we observe might be only a shadow of a richer, higher dimensional reality. The three spatial dimensions we navigate could be an emergent projection of something far more complex, existing in realms beyond our direct perception. This raises profound questions about the pre-Big Bang state. If extra dimensions exist, what role did they play in shaping the universe? Inflation was once thought to be a one-time, brief period of exponential expansion that triggered the Big Bang. But the mathematics suggests something stranger. Inflation is driven by a quantum field called the When the field sits at a high energy value, space expands exponentially. As the field rolls down toward lower energy, inflation slows and eventually ends, converting its energy into matter and radiation. The Big Bang we observe, quantum fluctuations, however, can perturb the inflated field. In some regions, fluctuations push it back to higher energy before it fully rolls down, causing inflation to continue locally. In other regions, inflation ends, producing hot Big Bang conditions. This creates a fractal structure. Our observable universe is just a pocket where inflation ended, while regions beyond our cosmic horizon are still inflating. Each new pocket that ends inflation becomes its own Big Bang universe, capable of forming galaxies, stars, and potentially life. The process never stops. Supernal inflation continuously spawns an infinite number of pocket universes. Alan Guth and Andre Linde developed this framework in the 1980s, and it emerges naturally from combining inflation with quantum mechanics. The implications are staggering. There isn't just one universe. There may be an infinite multiverse, with each bubble universe potentially having different properties. Quantum fluctuations could also vary the physical constants in each pocket, creating universes with different laws of physics. This explains why our universe has life-permitting constants out of infinite possibilities. We find ourselves in a universe compatible with our existence, yet this picture creates an observability problem. We can only see inside our own bubble. The inflating space between bubbles expands faster than light, so no signal from another pocket can ever reach us. Each pocket is causally disconnected, fundamentally isolated. Some argue this makes the multiverse unscientific, as we cannot directly test other bubbles. Others contend that the multiverse is a necessary consequence of testable physics. If inflation is correct, eternal inflation follows inevitably. Rejecting the multiverse would require rejecting confirmed physical theories. Observationally, We are confined to our pocket universe. We can measure its properties map, the cosmic microwave background, determine the expansion rate, quantify dark energy, but whether other bubbles exist remains unknown. If they do, then our Big Bang was not the origin of inflation, merely the end of inflation in our local region. Other regions ended inflation earlier or later, and some may never stop. There is no universal before the Big Bang. Each pocket has its own timeline, its own origin, its own history. Modern cosmology paints a layered, complex reality rather than a simple creation story. For decades, the Big Bang singularity was treated as physically real, a point of infinite density, temperature, and curvature. But physicists never believed this. A singularity signals the breakdown of a theory, not reality itself. General relativity predicts singularities because it is a classical theory. It ignores quantum effects, which dominate at small scales and high energies, just as classical fluid mechanics fails at the molecular level. General relativity fails at the Planck scale, 10,3510, 351035 meters, 104310, 431043 seconds. Energies around 1019, 10100, 91,000, 19 GeV. At this scale, space and time fluctuate, distance and duration become uncertain, and quantum mechanics forbids true singularities. The Hawking-Penrose singularity theorems showed where general relativity inevitably fails, highlighting the need for quantum gravity. Loop quantum gravity replaces the singularity with a bounce. String theory might enforce a minimum size. Other quantum gravity models offer their own solutions. The common conclusion: the singularity isn't real. The Big Bang wasn't the universe springing from nothing. It was a transition between quantum states. The pre-transition state could have been a contracting universe, an inflating vacuum, or a higher dimensional configuration, but it was something, not nothing. This reframing shifts the question. We aren't seeking how something emerged from absolute nothing. Instead, we ask what the pre-Big Bang quantum state was and why it transitioned into our current expanding universe. Though we don't fully understand quantum gravity or the details of this transition, we know that infinite density is unphysical. The task is now to explain the nature of the pre-Big Bang state, a challenging but tractable problem. Quantum mechanics and general relativity remain exquisitely tested. Quantum mechanics predicts atoms, lasers, and electronics with perfect accuracy. General relativity predicts planetary orbits, light bending, and gravitational waves flawlessly. Both work in their domains, but they clash fundamentally when combined. In quantum mechanics, time is a uniform background parameter, and particles exist in general relativity, time is part of space-time, which curves with mass and energy, and space-time has a definite geometry. Reconciling these frameworks at extreme scales remains the central challenge of modern theoretical physics. At the Planck scale, the contradictions between quantum mechanics and general relativity become unavoidable. You can't have space-time in a superposition of different curvatures, or can you? This is where a theory of quantum gravity becomes essential, a framework that consistently unites the principles of both quantum mechanics and gravity. No complete, universally accepted version exists yet, but several promising approaches are under active development. String theory replaces point particles with tiny vibrating strings, smoothing out the singularities that arise in quantum gravity calculations. Its mathematics is elegant and has the potential to describe all forces and particles within a single framework. However, it requires extra dimensions, has an enormous landscape of possible solutions, and makes few testable predictions at accessible energies. Loop quantum gravity takes a different route, quantizing space-time itself as a network of discrete loops. This approach avoids singularities and explains how space emerges from fundamental quantum building blocks. But it struggles to incorporate matter and forces beyond gravity, and connecting it to particle physics remains challenging. Other approaches include causal dynamical triangulations, which build space-time from simple geometric pieces and evolve them with quantum rules. Asymptotic safety, which suggests gravity may remain well-behaved at high energies due to a special mathematical property. And emergent gravity theories, which propose that space-time is not fundamental but arises from deeper quantum information. Each approach has its strengths, its weaknesses, and distinct predictions for Planck-scale physics. Testing any of them directly is nearly impossible with current technology. The scales are too small. The energies too high. Cosmology, however, offers an indirect laboratory. The early universe naturally probed Planck-scale physics. By analyzing the cosmic microwave background, gravitational waves, and the large-scale structure of the universe, we may decode subtle fingerprints left by quantum gravity, offering clues about which theory is correct. Understanding the pre-Big Bang universe is thus not just philosophical. Is a window into the most fundamental laws of physics. One of the most striking mathematical tools in this quest is the Wheeler-DeWitt equation, derived by John Wheeler and Bryce DeWitt in 1967. This equation attempts to describe the quantum state of the entire universe. Like an electron's wave function describes the probabilities of its positions, the Wheeler-DeWitt equation describes the possible configurations of the universe itself. Remarkably, the equation contains no explicit time variable. Instead, it encodes relationships between different aspects of the universe's state, raising deep questions about whether time is fundamental or emergent. Applied to cosmology, the Wheeler-DeWitt equation allows solutions where the universe tunnels into existence from a state with zero classical size. This is not metaphorical. It is a genuine quantum tunneling process. Similar to how particles can penetrate energy barriers they cannot cross classically. In Alexander Vilenkin's universe, from nothing framework, the nothing is a quantum vacuum state with no classical space-time. Through tunneling, this vacuum can jump to a small, closed configuration that immediately begins inflating. From the perspective of an observer inside the universe, time appears to begin at the moment of tunneling. But calling this nothing is misleading. The quantum vacuum is real, has properties, and is governed by mathematical laws. It is the quantum ground state preceding classical space-time. Other solutions to the Wheeler-DeWitt equation offer additional insights. The Hartle-Hawking no-boundary proposal uses imaginary time to smooth out singularities. Bohmian pilot wave interpretations suggest that the quantum potential in the equation acts like an effective cosmological constant. Chinese physicists Dong Shanhai, Dong Fangao, and Qing Kai explored spontaneous creation scenarios, showing that under certain conditions, a Planck-sized vacuum bubble has a non-zero quantum probability of expanding rather than collapsing. While tiny, these probabilities become actual outcomes in a timeless quantum realm where all possibilities exist in superposa, in an eternal quantum foam of fluctuating vacuum states. Every possible configuration eventually occurs. This provides a mechanism for the universe's origin that requires no external cause. The quantum vacuum is inherently unstable. Virtual fluctuations constantly occur, most collapsing immediately, but occasionally, by chance, one grows into an inflationary bubble that becomes a universe. The universe arises naturally from the properties of quantum mechanics itself, eliminating the need for a singularity or an absolute nothing. The Wheeler-DeWitt equation is not a complete theory. It assumes a particular form of quantum mechanics and does not incorporate the full machinery of quantum field theory. Yet it demonstrates that mathematics allows universes to spontaneously emerge from quantum states. Whether nature actually uses this mechanism remains unknown. Testing these ideas is extraordinarily difficult. We cannot directly observe the wave function of the universe. We are inside it, part of it. We only see its consequences, the structure of space-time, the distribution of matter, the cosmic expansion. The underlying quantum state itself remains hidden. Still, the implications are profound. The universe's origin might have been a purely quantum event, requiring no external trigger. The laws of physics themselves may suffice to explain existence. Step back from the details, and the landscape of modern theories reveals a common theme. None require an absolute beginning. Whether it's inflation preceding the Big Bang, cyclic bounces, epiotic collisions, eternal inflation, quantum tunneling via the Wheeler-DeWitt equation, or loop quantum gravity bridges each framework presents a universe without a first moment. The Big Bang was not creation. It was transformation. Something always came before it. An inflating vacuum, a contracting universe, quantum foam, or even a higher dimensional configuration. The chain of causation may extend infinitely into the past, with no first cause, no moment of creation, no absolute beginning. This challenges human intuition, accustomed to stories with clear beginnings. But nature does not conform to narrative preferences. If the mathematics implies time is eternal, then time is eternal. Alternatively, time may be cyclic or emergent. Roger Penrose's conformal cyclic cosmology envisions the infinite future of one cosmic epoch, becoming the Big Bang of the next. Julian Barber proposes that time emerges from changing configurations rather than being fundamental. Both perspectives suggest that a linear, absolute start to time is naive. The philosophical implications are staggering. If the universe has no beginning, then asking why it exists may be the wrong question. Existence is the default. True nothingness, state with no fields, no vacuum energy, no quantum fluctuations, no space-time, no laws may be impossible. Quantum mechanics, the uncertainty principle, and the structure of mathematics itself forbid it. Reality, at its deepest level, is never empty. It is a dynamic system of fields, probabilities, and geometry in constant evolution. The universe transforms continuously, expanding, contracting, bouncing, inflating, generating structure, dissipating into radiation, and repeating. Each phase appears different, but the underlying reality persists. We exist in an expanding phase, seeded by a hot Big Bang, itself preceded by a cold inflationary epoch. Trillions of years from now, dark energy might dominate, diluting matter and leaving a cold, empty cosmos. But this is not an end, merely another phase transition. Colliding branes, quantum tunneling, or loop quantum bounces could trigger new epochs. The universe continues, just in different forms. This view aligns with deeper principles of physics. Energy is conserved. Information may be conserved. Fundamental constants remain constant. Why would such structured laws suddenly emerge from absolute nothing or vanish into it? They wouldn't. The universe does not begin or end. It transforms, following principles we are gradually uncovering through observation, experiment, and mathematics. The question shifts. Not why is there something rather than nothing, but why does the universe take this particular form right now? The answer lies in quantum mechanics, gravity, vacuum energy, inflation, and possibly higher dimensions. It lies in the mathematics describing evolving fields, curving space-time, and probabilities collapsing into reality. It lies in natural law, not supernatural intervention. In physical process, not metaphysical mystery. The cosmos is not a creation. It is an eternal pattern of change, sometimes expanding, sometimes contracting, sometimes inflating, sometimes bouncing, always transforming, always existing, never truly beginning or ending. We are part of this transformation, temporary arrangements of atoms, shaped by the aftermath of one particular Big Bang. One moment in one region of an infinite multiverse, or one cycle in an eternal recurrence. Our awareness is brief, our curiosity a fleeting spark, yet we glimpse a vast, strange reality. The universe is far older, far larger, and far stranger than we imagined. Our Big Bang was not the start of everything. It was barely a start at all. Just one transition in a reality that has no beginning and needs none. Nothing never existed. The void was never empty. Reality is eternal transformation. We are witnessing one fleeting phase of it. That is what existed before the Big Bang. That is what exists now. And that is what will exist forever. Not nothing, everything.